Good?
Yeah.
All right. Anyways, so recap real quick since we just turned on the camera for when you guys watch this. If you ever watch it. Proving that limit of a(n) to the n equals 0, given that a(n) converges to a and the absolute value of a is less than 1. So what I just was explaining to you is that there's two main ideas that we're using. The first idea that we're going to use is this proof. If the absolute value of c is less than 1, then the limit of c to the n equals 0. That was something that was proved in section 2.3. And then once we have that, we're going to use the comparison limit. The comparison limit is if bn converges to b, and if the distance between an and a is less than or equal to the distance between bn and b from some index onwards by some constant factor, then the limit of an equals a. So here's a comparison limit. Here's, I don't know the name of this theorem, but that theorem. Those are the two theorems that we're going to be using in this proof. So our goal is to find a c such that the absolute value of an is less than c is less than 1. That way we can use the comparison limit on these two things to the n. Right? So when we put this to the n and this to the n, this is still less than this, and then we know that this goes to 0, so then this thing is going to go to 0. Which is what we're trying to prove. So that's a quick recap, so let's get to where we are in the proof. So I know that a converges to a. So that means that since the limit of a converges to a, then there exists some index n such that an minus a is less than 1 minus, it's kind of implied, but yeah, from some index onwards. And remember, this number then, so when we look at our number line again, so here's 0, here's 1, here's negative 1. We know that a is in between negative 1 and 1, so a could either be, we'll think about those two cases, a is up here, a is down here. This then is half this distance, at 1 minus the absolute value of a. This distance and this distance are the same, if a is positive or negative. So this distance is 1 minus a over 2, and then if you do the absolute value, then it's going to give you the same number here, so it's always a positive number. Okay? So that's where that number comes from, it's half that distance. Alright. So now, remember where we're trying to get. We're trying to find a c. This is not our c, this is just something that we know. We need to find this c. We need to use the fact that a minus a is less than this number to get absolute value of an is less than something that's always a positive number. Okay?
Use the absolute value then.
Right, so the next thing would be then we want to get rid of this absolute value sign here, right? So let's get rid of that absolute value sign here. How do we do that? We do well, I'll just write it out and then you'll see. Negative 1 plus the absolute value of a over 2, the negative of this thing, is less than an minus a is less than 1 minus the absolute value of a over 2. You remember that? Okay, so nothing weird there. Okay, now I need an is less than something. I need to handle both, well, maybe we'll write this one more way. We'll shift the a's to both sides, and then we'll handle the positive and negative case. So we get I made a plus a to both sides real quick. A is not always positive. It can be positive or negative. So I get negative 1 plus the absolute value of a plus 2a over 2 is less than an is less than 1 minus absolute value of a plus 2a over 2. You get with that? Plus a to both sides? Okay. So now we'll handle both cases. We'll handle the positive case and the negative case. Not the positive. We'll handle the non-negative case and then the negative case. So the non-negative case. If a is greater than or equal to 0, we'll handle that case first. Then what do we get? So looking at this, now a is greater than or equal to 0. So what's the absolute value of a? A. Perfect. So rewriting this, what do we get? We get negative 1 plus 3a over 2 is less than an is less than 1 minus a plus 2a is plus a over 2. Good? Now remember what I'm trying to get. I'm trying to get absolute value of an is less than a number that's less than 1. Is this number less than 1?
Yeah.
So now I need to get the absolute value of an is less than this thing.
We know that's less than 1 because we know a is always less than 1. And 1 plus something less than 1 over 2 is always less than 1.
I know that an is less than something that's less than 1. Now I need absolute value of an is less than something that's less than 1. Okay?
I'm saying we know that that's less than 1 because a is less than 1.
Oh, yes. A is a positive number less than 1.
It can't be 1.
So this whole a is less than 1, so the sum up here is less than 2. Something smaller than 2 over 2 is less than 1. Okay. So, trying to help this next step be intuitive, but what I wish I had, so I can do an is less than, how can I motivate this better? Here's what I'm trying to get this to look like. An is less than 1 plus the absolute value of a over 2 is greater than negative 1 minus the absolute value of a over 2. If I had it like this, then I can go straight to absolute value of an is less than 1 plus absolute value of a over 2.
Yeah.
Okay? So, I'm trying to get it from this to this, because once I have this, then I have what I'm looking for.
Why do you need it in the absolute value though?
The absolute value of a there.
No, an. Isn't that what the motive for that is? Because can't you just...
I'm ultimately using the comparison limit. Remember the comparison limit.
Oh yeah.
When I use my comparison limit, it's going to be an minus 0, because I'm proving an converges to 0. So this and an minus 0 are the same thing. I'm proving that the limit of this thing is equal to 0 when I take it to the end. So that's why I need the absolute value of an, not just an. Does that make sense? And it makes a huge difference. Showing that a sequence is less than 1 is drastically different than showing that the absolute value of a sequence is less than 1. Right?
No.
Because that sequence could have gone off to negative infinity.
Oh, right. Yeah.
So those are saying drastically different things. Anyways, so here's what I'm trying to get. Here's what I have to work with. Well, isn't this less than this?
No.
This is some number plus 3a. This is some number, the same number, minus an a.
Yeah, but a can be negative.
It's positive in this case.
Oh yeah.
So here's the big leap I want to make that I'm so worried about making without losing it. Negative 1 minus a over 2 is less than, this is less than an is less than 1 plus a over 2. That's a big leap I want to make that I'm afraid to
Can't
make.
make that leap. Can't make that leap.
This is less than this.
Yeah.
Is less than this.
Right. Okay, yeah. I guess you can make that leap. Okay.
Good? Sorry, erasing, well, we'll just use a lot of vertical space. Okay, so that is true. What does that give us? Well, that gives us
We got that.
negative 1 minus the absolute value of a over 2 is less than an is less than 1 plus the absolute value of a over 2, which gives us absolute value of an is less than 1 plus absolute value of a over 2, which is what we want. Now I need to show that I get the same exact result in the negative case as well. Good? Alright, so let's do the negative case. For if a is less than 0, comma, let's see, what were we doing? where did we initially start? We initially started here. Okay, so now if a is less than 0, what's the absolute value of a?
It's negative A.
Oh, marker at face.
Negative
Draw a
A.
mustache on in the process. Alright. It's negative a. So I'm applying the absolute values here and here, and I'm going to rewrite that, and don't let this confuse you. So now I have negative 1 plus a over 2 is less than an is less than 1
minus A.
Plus
Where are we
3A.
looking?
plus 3a.
Oh, up there, yeah.
We're looking at this. And I was
so-
plugging in minus a for the absolute value.
If A is negative,
If a is negative, then negative absolute value of a
it's
is
going to be positive.
Oh my gosh.
don't know what you mean by that.
Well, I'm saying.
It's not going to have a negative symbol in front of it, but a is a negative number.
Yeah, I got that.
Okay. So this is just a plus 2 more a gives me 3a. We good up to there? Now we're doing the exact same type of thing. Maybe I'll just tack it on right here instead of doing what I did last time. This is less than 1. Let's see, what am I going to ultimately want?
1 plus.
1, I think I'm going to want minus a
Yeah.
over 2. 1 plus 3 of a negative number is definitely less than 1 minus a negative number.
Yeah.
Okay? Gonna rewrite the same inequality one more way that might seem kind of weird, but you'll see it, I hope, when I'm done.
I don't.
Rewrote the same inequality. You good with that?
Yeah.
No. Oh, never mind, yeah.
Alright. And then here's the big old leap that we're going to make. We get negative 1 minus the absolute value of a over 2 is less than an is less than, sorry, I need to get rid of this now. 1 plus the absolute value of a over 2. Right?
Mm-hmm.
And what does that give us?
Absolute value of A is less than 1 plus absolute value of A over 2.
Perfect.
We're supposed to think about these things.
I don't know, how do I think about it? My teacher taught me. Well, this is like the 3rd time I'm going over this problem with you guys, so.
I mean, I don't know.
Wonderful. So in either case, you got absolute value of an is less than something that we know is less than 1, right?
Mm-hmm.
Negative 1 minus absolute value of
Well, should we just jump right over to it? You write everything out for you guys so you can see that. Okay, a side note that we lost in translation. This inequality was true from some index onwards. And then I stopped saying that,
yeah.
but, so sorry about that. But it was only true for some index onwards. It wasn't always true. It was only true from some index onwards. is only true when I got this distance less than that distance. Right?
Yeah.
Any leaps there you don't like?
One second, I do have a question.
This one is interesting.
So why did we put over n in our last line?
Sorry, what?
Why did we put our term? So we found our c.
1 plus absolute value a over 2.
But our 0 is what we're what?
Oops. And we just use the comparison lemma, and away we go, right?
Oh, there we go. That is what it is. A n to the n equals 0.
Probably should have stated that this thing converges to 0, and then said, then this converges to 0 since this. Because this is where we're using the comparison method, right? We know that this thing converges to this thing if this thing converges to this thing. If this inequality is true from summate that converse. Anything we're missing? Anything still fuzzy? Anything we need to go over again?
This
Not the best order to write the proof in, I admit, with those two lines, but it makes sense. It's not a big deal. Is that how you feel about your work?
I want to try to reproduce it. But now let's go into conversions.
What do you mean going to convergence? That's like all we've been doing.
Or
Continuity. Consistency. Consistency is what we tackled in geometry.
Yeah, I remember that.
No, you don't. Are you good?
I'm looking it over.
Alright, look it over. Let me know when you're done looking it over.
This is like the ultimate showdown.
This literally kills me.
Well, that's too bad. Hate to see you die. It's nice knowing you.
It took me 2.5 hours last time to do this one problem. I did my whole test in 30 minutes, except for this.
It makes sense. There are way too many logical leaps here. Trying to manipulate a term to get it to
Logical
turn
leaps.
out. Oh, that's just like
Well,
oh.
yeah, there was some playing with the numbers to make it do what you wanted it to do. But big picture, what was I trying to show?
That if we can find a number that is less than
That the absolute
1
value of
to
n
a,
is less
what is
than
the distance? A path.
something
I mean,
less than.
okay, here's how we could have motivated these numbers one more way to help you see where they came from. Because I knew that these numbers should have been the numbers that we're seeing here. So the first number, we already went over how we got that. Right? Let's draw our number line. Here's 0. Here's -1. Here's 1. A is either here or A is either here. The first number that we talked about, this number, that was calculating half this distance. Right? Or half this distance. The number that we end up with then is this number right here or this number right here.
Right.
So if it's within this distance,
It's less
then the absolute value is less than this number or this number. Right? If it's within this distance, absolute value is less than that. If it's within this distance, absolute value is less than that. What is that number right there?
It's less than 1.
That number, if a is positive, is 1 plus a over 2. If that number is negative, it's 1, well, it's just a over 2. Why am I saying over 2? Sorry. It's the midpoint of those two things. I was doing it right in both cases. Negative 1 plus a over 2 if it's negative. It's the midpoint. That's the midpoint. The midpoint. In both cases, the absolute value of it we could have written this way. 1 plus absolute value of a over 2.
Right. And this number.
So I knew that that's the number I was going to end up with, which is how I knew I was going to force that to come out. And the distance I knew I was starting with is that. So I knew that this should be the number coming out if this is the distance I'm using. Does that make sense?
Yeah.
So when you know what you're trying to get to show up, when you know what should show up, it shouldn't be that, I don't know.
I get it. I get it.
Definitely the hardest part was to come up with that number for me.
What is this man doing?
Don't worry about it. Just trying to take care of some trees.
I just think it's more about the universe.
Maybe get a sample or something.
Photographs.
Huh?
Alright,
Photographs.
we're not worried about that. We're worried about this. Does this make sense?
Yeah.
Logic of it does, yeah.
Well, what doesn't make sense if the logic makes sense? Well, try reproducing it. Make sure you can reproduce it. That's how you ensure that you understand it. And you'll figure out where you get stuck. You can ask me questions. You can rewatch me reproduce online, I guess. If you get stuck, use that to help you figure out what to do next. But yeah, so I guess that was the hardest problem on your test.
Yeah.
Yeah.
Okay, so are we ready to move on now? With
Consistency.
consistency. Yeah, we'll consistently move forward to talk about continuity. And let's see. I started out with notation. Let's make sure you still remember the notation. So moving on with chapter 3 now. If I have F, D, R, what does this mean?
If
The
the
domain.
domain is in the real numbers. Right?
What's the way I could read that, first of all?
If the function has a domain in the real numbers.
No, this is a function f from D to R. Here's the domain, here's the codomain. The
Oh,
range
that's
is
the
always
range.
a subset of that. It's not the range is always a subset of that. It's a codomain.
Codomain.
And we won't say range, we'll say image. The image of the function is a subset of the right-hand set. The domain of the function is the left-hand set.
Why is it a subset?
Look at the function f from R to R by f of x equals x squared.
From
What's the image of this thing?
1, 2, 4, 8, 4, 16, 32.
Well, you're naming some elements in there, but the image of this thing is 0 to infinity. That's the image. Right?
Mm-hmm.
So this is the domain. This is the codomain, but the image is a subset of that thing, or the range is a subset of that thing. And that's what this notation means. And it's implied from here on out that when we use a D right there, we're talking about a subset of the real numbers.
Isn't it the domain? Am I wrong to think of this as the x and the y?
This is the domain, and this is the codomain.
Why?
This is all your x's, and all your y's are a subset of this thing,
You don't.
if
okay.
you want to think about
Are you
Okay.
saying that? I don't know what you mean by codomain.
Well,
You're not meaning the image per se, but
The
it can.
image is in there.
it's a subset.
Okay.
The codomain of this function is all real numbers,
Mm-hmm.
but you can't get -2. -2 is not in the range. You can't take a number, square it, and get -2. You can't take a real number, square it, and get -2.
So what does codomain mean? Just all real numbers?
It's the name of the set that we're mapping to.
Oh, okay. Okay.
So we're mapping from the real numbers to the real numbers.
Okay.
Okay? Good with that? Basic notation?
Mm-hmm.
What's up, James?
I'm wondering, how do you read that?
F is a function from D to R.
From the
And
domain
D
to the
is-
numbers.
D is the domain, and from here on out, we're assuming that D represents a subset of real numbers. The same way that we start just assuming anytime you see a capital N, that's a natural number. We're going to assume anytime you see D in this context, it represents a subset of real numbers. Not R, a subset of R.
All the real numbers.
Not all of them, a subset of them.
Nah, all of them.
No, for example, we might be looking at the function by this.
Oh yeah.
What's the domain here?
Oh yeah.
Everything except 0.
Right.
So we'll be talking, functions like this will be perfectly valid functions for us to talk about. But what does that mean? It means we can't have 0 in the domain.
So the domain of that function is all real numbers.
I-
Besides 0.
We can set up the function that way. You define the function how you want. If I were to write f from D to R by this, then you would probably assume that E is everything except 0. Right? Because that's the biggest subset of real numbers that we could use here to make this function still valid. To make this still a function, still defined.
Okay.
But just understanding the notation, f is a function from D to R. This is the domain, and it's going to be a subset of real numbers from here on out. That's what we're interested in from here on out are the real numbers, not the naturals, not the rationals. We're interested in the reals. Okay, so now, continuous. Remember what it means for a function to be continuous?
Yeah, it means you can't lift up your pen off the paper.
Now, has nothing to do with that.
No, it
Should say it has nothing to do with that. But no, that is not the definition of continuous. So let's write out the definition again. So, function f from some domain to the real numbers R is said to be continuous at, sorry, that's spaced at some real number x not in the domain provided that whenever the limit of xn equals x naught for some xn in D, maybe I should see how I actually wrote it instead of just coming up with a new way of writing on the fly. Provided that whenever xn is a sequence, indeed that converges to x naught. Yeah, that was a better way to say it. Alright, let's continue this. Continuous at x naught in D, provided that whenever this converges to x naught and it's in D, comma, then f of xn, the limit of this thing, is equal to f of x naught. Sorry, I did that weird. Curly braces in the wrong spot. F of x naught. So,
So if there's a sequence where the limit of it equals x naught,
here's how we'll think about it. I've got a function I'm wondering is it continuous at a point x naught? Alright,
What do you mean by x naught?
just some point in D. If D is 0 to 2, then x naught is just some number between 0 and 2.
right, and a function could be continuous at one point. Function's continuous at 1.
Right, so is a function continuous at x naught? How do we check that? We pick any sequence in D, xn, that converges to x naught. I said that bad.
No, I got that.
I know, but it doesn't make sense. I want to check if f is continuous at x naught in D. How do I do that? I need to show that for any sequence in xn that converges to x naught, then the image of that sequence converges to the image of x naught.
So it's kind of showing, like, back into the other sections, it's kind of showing you have a set S of real numbers, and then you go and you find an interval in that set that is continuous, making that set continuous, right? So, or it's like you have an interval AB, and then you have a set in it, or you have a set AN in it that converges, making, what am I trying to say?
I don't know, it
It's
almost sounds like
something
we're talking about
similar.
sequentially compact.
Yeah, sequentially.
So go back, we'll be using sequentially compact in the next section. So sequentially compact, what did that mean? So if I have some closed interval AB, in order for that to be sequentially compact, what does it mean for this to be sequentially compact? That means for any sequence in there, AN,
Then A converges to a number in there.
no, almost. For any sequence AN, it has a subsequence, ANK, whose limit we'll say is equal to C, that is in AB. So we proved that every sequence has a convergent subsequence. We already proved that. What does it mean for this to be sequentially compact? Pick any sequence in there. Then that sequence has a subsequence that converges to a point in there.
That's what I'm making my connection.
That's sequentially compact. This isn't quite the same thing. This is, okay, here's D. Here's D. Here's R. We want to know, we'll draw it like a number line. Here's x naught in there. Okay? For any sequence xn in here, so all of xn's in here, that converges to x naught, then the sequence, so these are your xn's. xn converging to x naught, right? Then f, remember what does f do? It maps E to R, right? And that means, so here's f of x naught. And then all these are your f of xn. So it's continuous at x naught if for any sequence in D that converges to x naught, the image of that sequence converges to the image of x naught. That feel like you made the leap? And once again, this is exactly what we did with that polynomial problem in like 2.2 or something like that. Strongly recommend you go and rewatch that problem. Try to wrap your head around that problem. If you can reproduce that problem, I highly doubt you'll have a problem with continuity in chapter 3.
In chapter 2 about the polynomial.
Yeah, we essentially proved all polynomials were continuous. Now that's not how it was set up. That's not the verbiage that they used, but it's essentially what we did. I don't remember what section it was in. I just remember when I was telling you guys that, then I said that that's what we were going to use to show that functions are continuous. Or I said something to that there. it's at the end of 2.1. So the last thing we did in 2.1. So if you can understand that, you'll be well anyway. Okay. So that was the definition of continuous. Good? All right, now let's do some simple proofs. Let's do a proof that some function that we know is continuous. So you can just see it in action. Prove that f from R to R by f of x is equal to x squared minus 2x plus 4 is continuous. Oh, I forgot to mention one more thing. This is what meant for the function to be continuous at a point. We call the function continuous if it's continuous at every point in its domain.
Which would be just xn, right?
No, xn is just an arbitrary sequence that converges to xn.
How do you prove that? It's
X
continuous
naught.
at every
So
single
every
point.
x naught it converges to every x naught.
How did you prove that? Any two even numbers added together is an even number.
Okay, let's see.
Yeah, let's see. You show that, well, yeah, we'll just see it. It's not complex. All right, so let's prove this. So first thing we need to do, keep looking at the wrong problem. Like, well, that's way more complicated than it needs to be. Okay. First thing we need to do, we need to pick some point out of the domain.
1.
Let x naught in R. It's any point in there.
Okay.
And if I can show it's always true for x naught, just knowing that's in R, that's true for every real number, right?
Yep.
Okay. And now you just almost use the definition directly. You could probably fill this out yourself if you thought about it, too.
F of x naught.
Then, or sorry. I need another left. Right? We need to pick some sequence, doesn't matter what sequence in R, that converges to x naught. Now, I can't remember, oh, it has to do with it being, R being dense. So we need to be careful for a second and justify the statement. R is dense. We showed that a logically equivalent of thinking about a set as dense is for any point you pick in a set, I can find a sequence that I almost said that wrong. To show that something is dense, we show that for any real number you pick, I can find a sequence in the dense set that converges to that real number.
Isn't it, if a set's dense, then I can find an interval where there's always a number.
That was the definition of dense. Then we showed it's logically equivalent. A logically equivalent way of thinking about dense set is,
If there's a sequence.
so here's my dense set. If for any real number you pick on the real number line, I can find a sequence in my dense set that I can find a sequence in my set that converges to that real number, then my set is dense. So I've got some set, I've got some real number. If for any real number you pick, I can always find a sequence in my set that converges to that real number, then my set is dense.
Right.
It's logically equivalent. It was an if and only if. So I know that R is dense, right?
Right.
And x naught's a real number. So I know that there exists some sequence xn that converges to x naught. Obviously.
Because R is
I could have used x naught, x naught, x naught, x naught, x naught, x naught. Could have used anything. But I need to show it's true for any, not for one. I need to show for any sequence xn that converges to x naught, then the image converges to the image.
Well, can't
So-
you say because R is dense? Always.
Yeah, we know that there's at least one sequence that converges to x naught. We're going to show from here on out that this works for any sequence that converges to x naught. And maybe that's even a point that we don't really need to make. This doesn't say that there needs to be one that works. It says for everyone that works. So maybe there was one. So maybe I stress that point too much. Anyways, continuing. 3. Alright. And the limit of f of xn, what does that equal?
The x naught, f of x
It
naught.
equals
F of x naught. The limit of f of x naught. Oh, sorry, just f of x naught.
It equals the limit of, come on you guys, what's our function?
Oh, the limit of x.
You guys are killing me. Equals the limit
4.
of xn squared minus 2xn plus 4. That's what f of xn is,
Oh, yeah, you're
right?
I'm not seeing it.
Oh, okay. You just plug in your.
Plug xn into that. What comes out?
Oh, you're putting x in. Okay.
Okay, we good now?
Yeah.
Alright, and I'm not going to write out each of the rules. We know that the limit of a product is a product of the limits. We know that the limit of the sum is the sum of the limits. We know the limit of difference is the difference of the limits. We're using all that in one go. So, this is equal to,
right. Limit of x n squared.
yeah, we'll write this. Maybe I'll do this one to make sure you see how we're handling the squared. Even though I won't do this again from here on out. You see how we would use all our limit rules over and over again to rewrite it that way?
Yeah.
And then finally, what is the limit of xn?
X naught.
X naught.
X naught! Wonderful! So now plug in our x naughts for all our limits of xn. What does that give us?
X naught.
X naught times
X naught squared minus 2x naught plus 4 is equal to f of x naught. Ta-da! We're done.
Okay, so walk me through this again.
Alright, taking your real number in the domain.
Okay.
We need to show that for any sequence that converges to this real number, the image of the sequence converges to the image of that number.
That's the definition of
Continuous.
if we find a number in xn, call it x naught, then
So to show that the function is continuous at x naught, we need to show that for any sequence xn that converges to x naught in our domain,
but how do we prove this for all the numbers?
x naught is any real number.
No, it's a real number.
It's any real number.
That sign means a real number.
What sign means?
Into your real number there. Number 1, let x be a real number.
The only property x naught has is a real number. It's a real number. In other words, plug in 2 for x naught. Ah, it works. Plug in 10 for x naught. Ah, it works. You can plug in any real number you want for x naught. X naught is just a real number. It's an arbitrary real number. It's representing some real number.
Okay.
Pick some real number. Doesn't matter which one. If it doesn't matter which one, that's true for all of them. So for any real number you pick some real number. It's like when we did epsilon. When we showed it was true for any epsilon, we weren't saying a particular epsilon. We're saying pick any epsilon you want, and I'll show it works. Same thing in here. Pick any real number you want. I'll show it's continuous at that real number. Therefore, it's continuous at all real numbers. Does that make sense?
I have a problem with what you just said. Pick any real number, therefore I'll show that it's continuous for all real numbers.
If this is true for any real number, it's true for all real numbers.
Yeah, but you
There's
said
2 ways
pick
of
any.
Huh?
You said pick any. And so I picked and you just prove it. That didn't prove them all.
any epsilon. It's like
If this is true for any, then this is true for all.
Okay.
Does that make sense?
Yeah.
It's actually 2 ways of reading the symbol. When I say for all x in R, the statement's true. Another way of reading that is for any x in R, the statement's true. So those are 2 logically equivalent ways of reading that statement. 2 different English interpretations of that statement.
So again, go over. If we find the domain
Okay, so let's go over what we're trying to do. We're trying to show that f is continuous. What does that mean? We're trying to show that it's continuous at every point in R, because this is a domain.
From the rails to the rails.
Yeah, it's from the rails to the rails. So the domain is all real numbers. So we need to show that it's continuous at every real number. Okay, so let x naught be some real number. And let xn be some sequence in the domain that converges to x naught. Then the image of the sequence better equal the image of x naught. If it does, it's continuous. If for any sequence you pick, the limit of the image of the sequence equals x naught, or equals the image of x naught, it's continuous.
Where would it not?
That's very simple.
We'll do an example of one where that doesn't happen next.
That seems simple.
But it's going to work for any polynomial function like that.
I feel
We
It's
already
not going
proved
to
that.
work for 1 over x.
So you're saying that any polynomial.
1 over x is continuous everywhere except at 0.
Are you gonna?
Because it's not defined at 0, so it can't be continuous or if it's not even defined.
But even like -1 over, or -1 to the n isn't continuous.
Are you saying that any polynomial function is continuous?
That one doesn't have a domain of rails. So that one's a little bit hard to talk about. Say that again.
Are you saying that any polynomial,
We already
Some
proved
polynomial
at the end of
are
2.1.
continuous.
We proved at the end of 2.1 that every polynomial function is continuous. That is what we proved.
Okay.
That just wasn't the terminology that we used. So we didn't use we used what the definition of this is directly instead of using the definition.
Okay.
We proved that for any sequence you had that converges to some real number, that the image of that sequence converges to the image of that real number when you apply the polynomial function. Because what's a polynomial function doing? All it's doing is multiplying and adding when you think about subtraction as adding. That's all polynomials do. And we already knew by the end of 2.1 that the limit of a product was a product of the limits, and the limit of a sum was a sum of the limits, and the limit of a constant was just a constant, which is all we needed to prove this.
Right.
Good? So that's not using anything real advanced, but there it is. Maybe I'll just erase this and do the next one and keep the definition there so that we can reference it. Alright, so next we want to prove that this function is continuous except at 0. So our function f from R to R by f of x equals 1 if x is greater than or equal to 0, 2 if x is less than 0. It's continuous everywhere but 0. Okay? Let's first show that it's not continuous at 0. How are we going to show that it's not continuous? We need to find some sequence
That in the domain that
converges to 0, but whose image does not converge to the image of 0. What's the image of 0?
0.
What's the image of 0?
Nothing.
What's the image of 0? What's f of 0?
1 or 2. Oh.
It's 0.
What do I get when I plug 0 into that function? 1! Holy cow! 1! The image of 0 is 1.
Oh.
So
Yeah.
I need to find a sequence in the domain whose image converges to something not 1. I need to find a sequence that converges to 0 whose image does not converge to 1. Obviously, just pick a negative sequence,
1 over
because
n.
then it will go to 2. So, 1. Observe that the limit of negative 1 over n is equal to 0. Right?
Mm-hmm.
positive, right? No, it's always negative. Okay, so what's the image of f of negative 1 over n?
You're actually confusing me with your questions.
Alright, I'm confusing you with my question. What do I get when I plug in negative 1 over n to the function?
You get
1. Negative 1.
Get 2.
I get 2. Is negative 1, or is 1 over n, is negative 1 over n always a negative number?
Yes.
I thought n is negative.
Yeah, I
No,
thought
n is just a natural number.
Okay.
This is a sequence. This is a sequence.
Right.
So you know exactly what the sequence is. Is it negative 1, negative 1 half, negative 1 third, negative 1 fourth, negative 1 fifth? That's what this is.
Yeah, I'm seeing it now.
You're seeing that? Okay, now we're going to take the image of this thing. What's the image of this thing? What's the image of negative 1 over n?
Negative 1 half, negative 1 fourth, negative 1.
No, it's,
Okay, what do I get when I plug negative 1 into here?
it's 2.
I'm confused with
Right.
that.
Look. X is less
Okay.
than 0.
Maybe we're doing this too fast. Okay. What is negative 1 over n? Okay, that is equal to negative 1, negative 1 half, negative 1 third, etc. What is f of negative 1 over n? What does this sequence look like? What's the first thing? What do I get when I plug negative 1 into this function?
You get 2.
2. Right. Oops. What do I get when I plug in negative 1 half to this function? 2. Okay. Are you guys with me now? Okay. So what is the image of this?
It's 2.
2.
So this is just equal to
2.
2. It's always 2. Forever 2. Maybe I did 2 steps in 1 there, but I think you can follow it now. So this is equal to 2. Is not equal to 1. Is equal to f at 0.
Not equal to 0.
It's not equal to 1. It's not equal to f of 0. The limit of the sequence equals 0, but the limit of the image does not equal the image of 0.
Okay, then so what? Why?
So it's not continuous at 0.
Oh, because it doesn't
It's
equal
not
1.
continuous at
I've
zero.
already-
Yeah, so I'm proving two things. I'm proving it's continuous everywhere but 0. So I'm proving it's not continuous at 0, and it's continuous anywhere else.
And you showed it's continuous to everywhere by.
I haven't shown that part yet.
Oh.
I started by showing it's not continuous at 0 to show you how
How
it's...
can't you say that whatever n you put in there will always be 2, so it's continuous? Whatever n.
When you talk about continuous, we're saying continuous at a point. So we're talking about, is this continuous at 0? Is it? Maybe drawing the image of this function real quick to help you. What does the graph of this thing look like?
It goes 1 and then skips down to 2.
It goes, let's see, the negatives are 2, right? Maybe put this line more centered. So here's 1, here's 2. This function is 2 when x is negative, 1 for 0 and positive. The way you saw that was we did an open circle, 2, closed circle, 1. That's what the function looks like. Right?
Okay.
So
Yeah.
big old obvious, yeah, it's not continuous at 0. Using the Jacob definition of continuity. Can you draw this thing without picking up your pencil? No, you can't.
If you're sly, you can go down the line and they won't see it.
Oh, so when you're proving it's continuous everywhere, then you have to take into account the other side, meaning 1.
Here's my question.
I don't know what you mean by the other side.
Okay, here's my question.
This is just a picture to help your intuition. Do not use a picture to prove. This helps intuition.
Okay.
Here's the definition. Use the definition. Understand the definition. This is nice. This is helpful. Don't rely on it. Doesn't always work. This always works. Because some things we can't draw pictures of. Right? I'll give you an example of when you can't draw a picture of. Can't graph that thing.
Again. Oh yeah, because irrational is dense, I remember. That's insane.
Okay? So don't rely on this, rely on this. Now, we needed to show two things. We've only shown one so far. We're showing that this function is not continuous at 0, and it's continuous everywhere that's not 0. Right?
Right.
So we just showed not 0.
So, this thing is not continuous at 0. How did we show that? We showed that there is some sequence that converges to 0, whose image does not converge to the image of 0. That's how we showed it. Because if it's continuous at a point,
Its image
that
converges
means
to the
for
same thing.
any sequence that converges to the point, the image of the sequence has to converge to the image of the point. That's what means to be continuous.
Oh, the image of the point, not the same point?
Yeah, the image of the point. Not the same point. This is not 0, this is f of 0.
Because f of 0 equals 1. Oh.
Yeah. So the sequence converges to 0, but the image of the sequence does not converge to the image of 0.
Oh!
If that were the case for any sequence, then it would have been continuous at 0. Just because what if we accidentally did this?
Then it'd be.
Then it would have worked,
Yeah.
right? So it's not that there aren't sequences that it works for. It's that if it doesn't work for every sequence, then it's not continuous at that point.
Right.
This is where I'm confused.
Okay, let's hear it.
This includes 0, which you proved because you just got rid of the 0 and it works. So,
I think you're
Would
mixing.
that
So
not
here's
make-
a function.
yes.
This is just a function,
Yes.
right? All right. Is this thing always negative?
Yes.
And it converges to 0.
Yes.
What is f of 0?
1.
So the image of this thing is always 2, since it's always negative.
Mm-hmm.
The image of 0 is 1. Those aren't the same thing.
Yeah, but then I don't understand, because if you just have the limit of 1 over n, then it works, which is in that sequence. Isn't it?
So what does the definition say?
Oh, you just proved that one of them doesn't work. So okay, I get it.
Clicking?
Yeah, okay.
Yeah,
Continue.
because it has to be true for every sequence.
one. Okay.
Right? It's like if I were to make the statement, every number is even. And you come along, you write 2, crap, yep. 4, crap, yep. 6, crap, yep. Must be true. I found infinite cases where it works. No, infinite cases is not proven in this class.
Okay.
It needs to be true for every case. And if there's even one case where it's not true, then you can't say the statement's true. So this is not continuous at 0, because there was at least one sequence that didn't work for. That make sense?
Yeah.
Okay. Now let's move on to the next part of the proof. It's continuous everywhere that's not 0. Let x naught in R such that x naught is not equal to 0. And maybe we'll just like break it up into the positive case and the negative case, and I'll just do one, doesn't matter which one, and you know how to do in that other case. So should we do positive or negative?
Negative.
Okay, so now x naught is less than 0. Let x n such that the limit of xn is equal to 0. Then the limit of f of xn maybe there comes a point that we need to, we've already had this discussion once, but let's remind ourselves of something that we proved in the past. Something that we proved in the past is, maybe you do it as a side note over here. If I know that the limit of an is equal to a is less than 0, then there comes a point where every sequence, there comes a point in the sequence where every term in the sequence after that is negative.
Right, yeah, we did.
Yeah.
Right? Similarly, if this were greater than 0, then there comes a point where every term in the sequence is greater than 0.
Mm-hmm.
Does that make sense? So I don't want to be too verbose in all my writing here.
Don't you just say there's a sub?
But in other words, that's another way that we could do it. If this is true, then there's a subsequence that's always negative, or a subsequence that's always positive. Maybe that's a fair way to think about it. So I won't write it out in words, but I'll just write it out so we'll use that idea. So the limit of this equals, maybe we'll mention it up here.
Subsequence B.
Let, huh?
I said the subsequence B.
Well, let x n such that the limit of x n equals that, comma, and let x and k be a subsequence of x n such that x and k is less than 0. You have that?
Mm-hmm.
Okay, so then we can talk about the limit of the sequence is equal to the limit of the subsequence if this converges. Do you remember that? If a sequence converges,
Then subsequence of
No,
Are you talking
it's
about that?
Wait, I don't see why we.
if a sequence converges, then every one of its subsequents converges to the same thing the
Oh,
sequence
yeah, I
converges to.
Mm-hmm.
Look,
That's the fact that we're going to use.
there's actually no guarantee we have a subsequence that is less than 0 because what if our sequence was always positive but converged to 0? Oh, that converges to
Oh, oops, not zeros. Thank you, thank you, thank you. X naught. Good question. Glad you're paying attention. That was a big uh-oh. X naught's less than 0, and x n converges to x naught, which is less than 0. Therefore, there is some subsequence of it that's always less than 0.
Right.
Good catch. Okay. Glad someone's paying attention. Janetta.
I'm trying to see it.
What did you change?
I had a 0 here instead of x naught by accident.
Then the limit.
Our definition is x n converges to x naught. Right? Okay, so the limit of f of x n is going to be the same thing as the limit of the subsequence, the image of the subsequence. And what does that equal?
Why is it then the limit? Why do those equal each other?
So if the sequence converges, then every subsequence converges to the same thing.
Right.
So the limit of a sequence and the limit of its subsequence are the same.
Right. What does that equal then?
Would it not be the limit of x naught?
What does that equal? No, it doesn't equal the limit of x naught. X naught is just a constant. It doesn't equal x naught. What?
0. It's going to be 1.
1! Almost! 2. X and k is always less than 0.
Oh yeah.
So anytime we plug in something less than 0 into that thing, we get 2.
Right.
Which is equal to f of x naught. Because x naught is less than 0. Ah, it worked!
Oh.
Dude.
And then the positive case would be real similar. We
It's
don't
like
grab
jumping
that out.
into 2 different like spheres. Range domain.
Yeah, and that is a good point to keep in your head at all times. We're going from one set of the domain to the codomain. And we're saying, since it has a property here, that property was carried over here. This sequence converges to a point here, and so this sequence converges to a point here. And so continuous functions maintain that property. It's like after you map everything using the function, your sequences that converge to a point still converge to a point in the new mapping. That's like the foundations of topology. It's talking about what continuous functions are. You talk about them in a much more abstract, much more lower level sense than this. But that's good intuition to keep in your head. So any questions there?
I'm wondering how come you can't prove or say that the limit of f of xn equals 2? How come you have to bring in that subsequence?
Just because this could have had positive terms in it. And so this isn't always 2.
But if x naught, if it converges to x naught and x naught.
We're proving it converges. Oh. It converges, if xn converges to x naught.
And
Okay.
x naught is less than 0, then wouldn't that make every...
No.
No.
It can go from a billion and converge to something less.
Right, yeah, we can start at a billion and we can converge to -1. That's a possible sequence. But that sequence will eventually have terms that are all negative.
Yeah, and
Which
that's
is our
subsequence.
And those all negative terms will converge to the same thing that the whole thing converges to. So we're saying, let's just get those negative ones and look at what those go to. Because it's easier for us to think about with our function.
Okay.
My question is, how can you say that okay, your x and k is less than 0. Okay, that's number 5. The last part of number 5 is where I am a little confused.
Okay, so...
But number 6 makes sense.
Okay, so it went. I didn't write this out all the way. We had a little conversation over here of a proof that we did. So a proof that we did is, and let's set up for the case we're talking about. If the limit of an equals a, and a is less than 0, then there comes a point in an where all its terms are negative.
Right. Okay.
So since xn converges to x naught, and x naught is less than 0, where did I put that? And x naught is less than 0. Then there comes a point in xn where all its terms are less than 0.
SS is a subset.
Okay.
And so we're taking some subsequence where all its terms are less than 0. Because we know that there's one that exists. We're saying drop off the first 10,000 terms or whatever it is. There's a subsequence we can use.
So don't we have to prove the positive side now?
Yeah, I'm saying I don't need to do the positive because it's the same as the negative.
Okay.
There's no point. It'll be the same thing.
We're going to do the same thing. There will come to a point where you have subsets that are all positive.
Yeah, so then if a were greater than a, okay, are you okay with the negative case? So let's make it a positive case real quick. You good with this?
Mm-hmm.
So let's make it positive. Assume xn is greater than 0. Well, then there exists this and this such that greater than 0. Then the limit of this equals 1, which is what f of x naught equals.
It'd be greater than or equal to?
No, we handled 0 separately. And then we handle everything greater than 0 and less than 0.
Yeah.
So we proved when it was less than 0 it was continuous, when it was greater than 0 it was continuous, and when it was 0 it was not continuous. That's what we proved. Which is pretty obvious looking at the function. Everything over here, yep, that's continuous. Everything over here, yep, that's continuous. Right at that point, nope, that's not continuous. Okay.
In your at 1, if x is greater than or equal to 0, if you just got rid of that equal to 0, then you could just end it at is continuous, right?
Yeah. Well, almost. Change my whole game to not
Yeah.
include 0. But then that would be continuous. Yes.
Okay.
Next. You gotta say it with the right tone.
Throw them at me.
I really wish you would have done that.
Wasn't sure if I so to use would. Alright, let's do another one. Need to go get some new markers.
The first time you said that in this class.
Huh?
I said that's like the first time you said that in this class.
That's like 100 times you said it.
Even forgot to say.
Here's he has some stash in here.
I think it's in the other drawer.
Oh, that's not. Okay, you just using the desk.
It's true.
I think there's some in that other drawer.
He saw that you
Only
did.
because that's where he always goes to get markers.
Oh yeah.
Bunch of pens in there, red pens. That's good to know. And extension cord. Hey! That can clean my setup a little bit. Because that is a mess. Good to know, good to know. It's nice when you actually look around the school you work at for some resources. Instead of trying to figure it all out yourself.
It doesn't look like there are any.
Literally went and bought red pens to grade your guys' papers. I know, I lose money being here. It's not even that I don't get paid. Alright. Next one. Next one is going to be that exact one. We're going to prove that that thing over there isn't continuous everywhere, but I don't remember if it is 0 and 1. Yeah, it was. Okay.
We can prove that it's not continuous everywhere.
Yeah, there's no point where that thing's continuous.
Just use the case that is 0.
Proving it's not continuous at 0 isn't the same thing as proving that it's not continuous anywhere.
Yeah.
Oh, did you do 1 or
1
0?
if x is in.
1 for rational, 0 for not. So 1 if it's rational,
Oh, rational.
0
Oh, that one. I didn't even notice that.
x is not if it's irrational.
Are we going to find contradicting statements?
No, we're just going to do the same thing we did with 0. We're going to prove that it's not continuous.
Well, it should be continuous at the rationals.
No! This function is not continuous anywhere. You cannot find a point where it's continuous.
Well, what I'm saying is, with 0, we were like, plug it in.
Sorry, I left off f from r to r.
Wait, you were telling me that this function isn't continuous anywhere?
You can't find a point where this function's continuous.
X is 1/2.
Okay, it's not continuous there.
Yeah, because it's. Okay.
Here's a sequence. So let's write it out. I'll find a sequence real quick.
find a sequence. I forgot.
Yeah, here's a sequence. So you said it 1/2, right? So I'll do
You can do all the irrational numbers.
1/2 plus the square root of 2 over n. There's an irrational, right? Okay. So the limit of this thing equals 1/2, right?
Yeah.
You know that so far? Okay, what's f of this thing? Let's look at this sequence. Let's look at the limit of f. Oops. The limit of f of 1/2 plus the square root of 2 over n.
0.
That's always irrational, is equal to 0, is not equal to 1, is equal to f at 1/2. So it's not continuous at 1/2.
Yep. I
So
forgot that we're dealing with sequences.
now just do that for every other real number and we'll be done.
Okay.
Alright, so we got two cases. X naught is either rational or it's irrational, right?
Yeah. It's rational.
Which one do you want to start with?
Rational. Let's be rational beings here.
Let X naught in Q. Now here comes that proof, or that theorem that we already talked about another way to think about dense sets.
If X is a subset, such that.
If I have a set, here's my set, here's a real number. If for any real number you pick, I can always find a sequence in my set such that that sequence converges to the real number, that sequence is dense in R.
Right.
Good? We also proved that both the rationals and irrationals are dense.
Right.
Alright. So 2. Since
Rationals is dense.
irrationals are dense.
Rational.
Irrationals.
See, we are finding
There exists xn in the irrationals such that
converges
the
to
limit exactly of xn equals x naught. Right?
Right. And then there was a theorem that says all rationals converge.
Well, we're done. Then the limit of f of xn is equal to xn in the irrationals, so that's always equal to 0, is not equal to 1, is equal to f of x naught.
Wait. Okay, I didn't see the logic there. I thought I did.
Okay.
Since irrationals are dense, there exists a sequence xn in the irrational such that the limit of xn equals x naught. Well, what's our x naught?
Oh, sorry. Sorry about that. X naught. Some rational number.
Oh, see, that's where I was.
Okay.
where I was
Yeah, sorry about that. So pick any rational number. Is a rational number a real number?
Yes.
Yeah, okay. So, since the irrationals are dense, there is some sequence of irrational numbers that converge to that number, x naught. So, xn is a sequence of irrational numbers whose limit is x naught, a rational number. It's perfectly fine.
Then the limit.
So then, f of xn, since all the xn's are irrational, f of xn is always 0.
Right.
Since x naught is rational, f of x naught is 1.
Right.
Okay.
And then obviously, if x is not in Q, then that's the same. So now we'll just mess with this to do the same thing. Let x naught in the irrationals are not rational, right? Since rationals are dense, there exists that in the rationals, such that the limit of that equals that, then this equals 1 is not equal to 0. And that gives us the next case. So we handled when it's rational and when it's irrational.
When you're asking us to prove whether it's continuous or not, do you want us to do both cases? Right?
Yeah, don't be lazy like me. I'm saving time in writing, especially since my marker's done. You want to murder a marker all the way? Let's start.
Okay, some products and quotients of continuous motions.
You good with that? Get down on your knees and tell me you like it.
Fall on your knees.
Home Alone.
Hold on.
Home Alone? You not seen Home Alone? Oh, you haven't? So you don't even know.
Well,
what
I
it
have
is?
seen it. I would not get that quote though.
It's the second Home Alone movie.
I've seen only number one.
Yeah, it's in the second one.
Missing out.
One is the greatest.
Number 2.
Number 2 is pretty solid. Well, it's hard to know. I watched it so long ago. I liked it when I watched it. That's why I can say it.
It should make.
I would guess I would still think it's pretty solid.
Thanks for guys in New York City. Then just as the house.
It was unrealistic as crap.
Okay, more notation. Well, let's actually do a break real quick so I can go get a new marker.
Donnie, do you drink coffee in the morning?
Some mornings.
Office will make you coffee.
I'm straight time already in that hair. I don't want to waste
story about when Merle ran over Hiram. And she was like, it was really good with the Suburban because it was lifted off the ground. And then she's like, that's why I like driving the Suburban over grass.
Because if she runs over a
It
kid.
was like, so you like driving the Suburban because if you were to run over a child, it wouldn't hurt the child as much. She's like, no, Anna has more control.
Parents are so good.
Who should not get heat because it feels good?
Feels great.
Ah, great.
I thought my emotional talk. Jake.
Oh, did Mr. Zink talk to you, Don? He
No.
said he would. We have devotional talks on Monday and Tuesday, and we have to get our outlines to you, and you have to approve them before we talk
To him.
to Don.
What?
Yeah.
We actually did a little bit weird today. Usually we use our church history teacher, but this year we used our upper elective teachers.
My devotional talk.
So all the art history already talked, all the creative writing talked, and all
And
the
mass media
mass
started.
media.
We're the only ones left.
Yeah. Well, yeah, we're the only ones.
What on earth? So, I am approving your talks.
You're approving our outline so that essentially the idea behind it is we're not getting up there with nothing to say. I don't even know. But yeah.
I want to give a talk.
We have to give you our outline and you have to say, okay, that's devotional worthy.
Yeah.
Okay, and when are you supposed to talk?
On Monday and Tuesday. So we'll probably
next week.
Yeah.
So
we'll
I'm being
email you.
told about this.
Well,
I won't even see you guys again until after it's all done.
well, you'll see us the morning of Tuesday.
Yeah.
But me and Janetta, you have to talk on Tuesday because we're going on Monday.
Okay.
I want to know it too. Embarrassing.
Have so much. This.
He'll think I'm
Send.
retarded. Dude, your talk is easy. Peas podge. Trees.
Yeah, I actually already have my game right here.
Okay, well,
We'll email you the outlines and then you just text us and tell us that we're
Oh, yeah.
yeah, you guys should have my email. It's on the syllabus. Email me by Friday.
Email you by Friday.
Yeah, especially you. Because my weekends are beyond full.
Why? Saturday and Sunday.
Saturday is one of my fullest days because it's also a regular work day for me. I have to worry about meeting at night as well.
You usually work.
You do 6 days a week.
No, I work 5 days a week, but I teach on Tuesdays.
Would you say you put in more than 40 hours?
Probably.
Or no, you're on a salary, it doesn't matter.
Yeah, you can't just work as long as you're producing. When you feel like you're not being productive anymore, stop. That's how I do it. I don't know what other people do. I guess I do a little more than 40 hours a week.
They have to reach certain deadlines.
Yeah, you have work cut out for you, but it's not obvious that you were really working on it. I mean, just because you don't accomplish what you thought you would accomplish, what does that mean? Does that mean you were slacking? Well, that's one of a lot of possibilities.
Right.
So, even if you report you didn't accomplish what you didn't do, even if it was because you were slacking, it's hard for anyone to really know that. Anyways. Some more notation that you're already familiar with, I think, but let's introduce it, make sure it makes sense. So if I have two functions, f and g, notice that they have the same domain,
To range.
and they're both real number or real value functions, right? But they have the same domain, that's the thing to note there. Then f plus g of x is just f of x plus g of x. And f times g of x is just f of x times g of x. And then, as long as the g of x isn't 0, then, as long as g of x isn't 0, then f over g of x is just the quotient f of x over g of x.
Notice how that's a notation. I see how that's like a.
We're defining what this means. F plus g of x
Is f of x over g of x?
is f of x plus g of x.
Oh.
Or f times g of x is f of x times g of x.
Seems like a distributive property.
No. Let's
these
do
are
a quick
functions.
example. Yeah, it's a function. So if I say f of x is equal to x squared minus 7, and g of x is equal to x cubed plus x squared minus 2. And later in my proof, I want to mention f plus g, that function. What is f plus g?
X
Well,
plus-
f plus g of x, if we want to talk about it like that, is just the sum of those. X cubed plus 2x squared minus 9.
Wouldn't there need to be a proof for that?
No, we're saying that's what we mean by this. What do we mean by this?
Oh.
We mean this and this.
Right. Okay.
So it's notation. That make sense?
Mm-hmm.
So just new notation. I don't know if this author uses it a lot, but it's very common to start using this type of notation rather than writing it out like this. Gives you shorthand, especially when you don't care about what the independent variable is.
Right.
Okay, so now, quick proof. If f is a continuous function from D to R, and g is a continuous function from D to R, then their sum and product are continuous functions from D to R, and their quotient is, as long as the denominator isn't 0. And this is just using our limit properties directly.
Okay.
So, let's prove it. Let xn and d such that the limit of xn equals x naught. I'm proving it's continuous at x naught, some point. Since f and g are continuous, then the limit of f of xn equals f of x naught, and the limit of g of xn equals g of x naught. Right?
Mm-hmm.
That's what it means for those to be continuous. And then so obviously the limit of the sum equals the sum of the limits. Take the limit, voila. The limit of the product equals the product of the limits. Take the limit, voila. And then the quotient of the limit equals the limit of the quotients as long as the thing in the bottom is never 0, which we specified up here, which is take the limits, voila, we're done. So those are all pretty straightforward, even though that was a lot of writing. Any questions on those? I can't hear you when you all talk at once. Sounds like the classroom's silent. Alright, corollary. Let P be a function from R to R, and Q be a function from R. That's the second time I did that. That's why
Never seen that.
that D's darker than it's the same thing. And, yeah, I don't know what it is that makes me do that. And Q is a function from R to R. Let that and that be polynomials. Then P over Q is a function is continuous, sorry. We need to find the, then from D to R is continuous. Where D is equal to the set of all x in R such that Q of x is not equal to 0. Okay, hopefully this makes pretty good sense. This is something that you did in like your trig class most likely. They would keep giving you rational functions like this. That's what we call these, by the way, rational functions. If it's polynomial or polynomial, we typically call them rational. So when you have a rational function, that we would often say find the domain of the rational function, and it would always be this. All the real numbers that didn't make the denominator 0.
Mm-hmm.
But as long as you restrict your denominator like this, then you're always left with a continuous function. Because we already know that polynomials are continuous. We didn't say that, did we?
You said it.
We proved it in 2.1 though. We proved all polynomial functions are continuous. And so this is saying the quotient of two polynomial functions is also continuous, as long as you're careful with the domain. That make sense?
Mm-hmm.
All right. One more definition and then one more proof for this section. Composition. You guys know what function composition is?
Composing functions.
Yeah, the little circle thing.
Oh, yeah. If I think they call it f of g of x.
That's exactly what we call it, f of g of x typically. For functions,
That's very Alabama when these problems.
f from d to r and g from u to r.
You did and again.
What is going on with that?
It's because you have a G right after. Or
Last time we had a q after it.
And g from u to r, where, and here's some more notation that we haven't talked about yet, so, where f of d is a subset of u, that's a subset, it's a subset of u, comma, we define g of f of x equal g of f of x. Okay, so let me point out something really quick weird that we did. First off, this f of d, that was weird. D is a set. I just plugged a set into a function. What do we use this notation for? We use this notation basically to represent the image. We're saying map everything in the set. So, for example, if I have the function f of x equals x squared from the real numbers to the real numbers, then I would say that f of its domain is equal to 0 to infinity. Or in this case, its domain was all the real numbers.
Okay.
Okay.
So it's just like x almost.
It's everything, it's the image, it's the range, it's a shorthand, it's a way of writing the range. It's all the values we would have gotten if we would have plugged everything in D in. That's what that means.
Is a subset of u or is less than or equal to u?
A subset. This is a set. Up here it was this set. All the numbers from 0 to infinity. That's a subset of u. Why are we saying that this is a subset of u? Here's what we're saying. We're saying after you map f, I need to be able to pass it into g. I need to be able to pass f of x into g. G can only take things from u. So f of x needs to still be in u. So everything that comes out of f needs to be in u. Does that make sense?
Yeah.
Hopefully you're all fairly comfortable with function composition by now. So that
Yeah, but every
that's
time
what we do.
in that, we just assumed that d was all the real numbers.
Yeah, we'll be a little bit more careful with domains and images now, but the actual idea of composition hopefully isn't too weird. Let's just do an example real quick to see it in action. So let's say f of x equals x squared minus 2, and let's do g of x equals
X over 2.
x plus 9. Okay? So then F composed with, well, let's do the example we did first. G composed with F, and then we'll do it the other way. So then G composed with F
It's going to be x squared minus 2,
X
x squared plus 7,
is,
X cubed.
x squared plus 7.
well, let's just be very explicit for a second. Anyone have any issues with anything that happened in there?
Yeah,
Yeah, very much so.
you did it way.
Oh, I plugged in the wrong one.
Yeah, it's like, what? Minus 2.
Whoa, I did all sorts of
You screwed up so many things.
I screwed up so many things.
Plus 9.
Plus 9.
Okay. Now does anyone take issue with it? Alright, let's do the other one real quick. F composed with G of X is equal to F of G of X is equal to F of G of X is equal to
Squared. We'll need, that's good.
You mean 81?
18. Should be 18.
Oh, 17.
Plus 81 minus 2, which is 79.
anyone take issue with that? Big point to note, obviously those are two very different things. So order matters in function composition, or in other words, function composition is not
Consistent.
Uh,
Equal.
commutative.
Here we go.
That one.
What is with you and consistent?
It's got to be consistent in use of the word.
That's it.
Where am I going? Okay, so that's function composition. Now let's do our proof of function composition being continuous. Or we're proving it's not continuous. Wait, which one? Are we proving it's continuous or not continuous?
We are proving that it is.
I'm not saying look it up, I'm saying think about it.
That it is continuous. Bless you.
There is
You
something
literally have a brain
in my
damage.
muscle memory that will not let me do that.
It's the 4th time.
Sorry, shoot. I was supposed to write my statement there. Let's prove that function composition is continuous. I won't write what I'm proving, but that's like number 1, right? Let f from D to R and G from U to R be continuous functions. We're proving that f composed with, or that G composed with f. Here's what we're proving.
Continuous.
We're proving that G composed with f of x is
Since
continuous.
U is a subset of the domain, then.
Well, that's what we're proving is continuous, right?
Okay.
Let x not in D and let xn in D such that the limit of xn equals x naught. Now, ultimately, where are we trying to get? We're trying to get that the limit of G composed with f of xn is equal to G composed with f of x naught, right? That's going to be what we're trying to get to so that this whole thing is continuous.
Mm-hmm.
Okay. 3, since f is continuous, then the limit of f of xn, the limit of f of xn is equal to f of x naught.
Same thing with G.
For observe that, oh, I didn't finish writing this. Let f from d to r and g from u to r be continuous with f of d a subset of u.
Right.
Right? Otherwise I can't compose these two functions. It's only defined when that's the case. Otherwise function composition doesn't make sense. Okay, so we have two continuous functions where the image of one is a subset of the domain of the other. Okay? Observe that f of xn is a sequence in U and f of x naught is in U.
Yeah.
5. Since G is continuous, then the limit of G of f of xn is equal to
G of U.
G of f of x naught. Here's my point, here's my sequence. Since G is continuous, the limit of the sequence is equal to, since G is continuous, the image of the sequence, the limit of the image of the sequence is equal to the image of the point. Right? Now here's my point and here's my sequence. So first we had, here's my point, here's my sequence. Therefore the limit of the image of the sequence equaled the image of the point. Now here's my sequence, here's my point, and once again the limit of the image of the sequence is equal to the image of the point.
Okay.
You good with that?
Mm-hmm.
Yeah.
I don't know, we're done. That's what we were trying to get. I mean, I could have rewritten this in this notation. Same thing. Right? That we're saying the same thing. Okay. So function composition maintains continuity. That's the end of the first section.
The extreme value theorem.
Yeah, next is the extreme value theorem, which is a nice quick section. I think we can whack through it real quick.
Do you have the syllabus?
Huh?
Do you have the syllabus here?
No, it's on my laptop.
Did you email us the syllabus?
Pretty sure. Seems like something I do.
Yes, you did.
Alright, so talk about a minimum and a maximum real quick. So let f be a function from d to r. So if I have a function from d to r, then we said this function attains a maximum if the set f of d has a max, and it contains a minimum if this set f of d has a minimum. Pretty straightforward concept. So that's what we mean by a max and a min. Good with that? And the x naught that makes us reach its max, we call a maximizer, and the x that makes it reach a min, we call a minimizer. We already used a similar concept with sequences. Now we're just talking about the image of a function. You good with that? Okay. Then they want to do two examples showing that not all functions domain have a min and have a max. So let's see a function real quick that never attains the minimum or maximum. So if I have f from 0 to 1 to the real numbers by f of x is equal to 2x.
That's a minimum and maximum.
What's f of d? What's f of the domain? Maybe this is a weird way to write it.
0 to infinity.
No, it's just 0 to 2.
Right.
We're just multiplying everything by 2. So here's the entire image, right? Does this attain a max?
2.
No, that's a supremum. It doesn't have a max. Remember, if it has a max, that means it contains a supremum. If it has a min, that means it contains its infimum. There is no biggest element in this set.
Oh.
What's the biggest thing in there? You said 2. 2's not in there.
Why? Yeah, it is, because 2 times 1 is
No,
2.
it's an open.
1's not in there. That's an open interval. This is all the numbers between 0 and 1, not including 0 and 1.
Yeah, bogus.
This is all the numbers between 0 and 2, not including 0 and 2.
Yeah, same idea.
Same idea. So we all good there?
Yeah.
Okay, so that's one way that it doesn't attain a maximum or a minimum. The other example that they do is f from, let's see, f from 0 to 1 to r by f of x equals 1 over x. What's the image of this function? Another way I always say the image of the function is
1 to 0.
not use this weird notation, it's just the image of f
0 to 1.
is equal to,
0 to 1.
no, the smallest thing I can get in there is 1.
Oh,
It
1.
goes from 1 to infinity. Once again, that thing does not obtain a maximum because it's not bounded. Here it didn't attain a max because it didn't contain its supremum. Here it doesn't attain a max because it's not bounded. Plug in a really, really small number here, and you get something massive.
The infimum. What's that down there?
This?
Yeah.
That just means the image of f.
Oh.
That's instead of writing this weird notation.
But that one doesn't have a max or minimum?
No. From 1 to infinity?
Okay, yeah, it doesn't.
Yeah, it doesn't have a max because it's not even bounded. And it doesn't have a min because it doesn't include 1.
I don't see what you're trying to say.
These are examples of functions that don't have maximums and minimums.
They're the same with sequences.
It's a very similar thought process to sequences. Because now we're going to get the extreme value theorem. And the extreme value theorem says if f from a closed interval to R is continuous, then it has a max and min. Max and Does that make sense? So that's what we're going to prove in this section. Good? So the way that they do this is first they're going to do a little lemma, and then, well, here's the lemma. The first lemma that we're going to do is that, let's see, it's bounded, and then we'll show it contains a supremum. So we're going to prove this thing in 2 steps with 2 proofs. So the first proof we're going to do is
Why do we need 2 proofs?
just to break up into logical steps. So first we'll do a little lemma, and then we'll do the actual proof of it. So do you remember what a lemma is?
Yeah.
Yeah, it's like a small proof that helps you in your main proof. So if f is a function from a to b, from ab to r, is continuous, the image of, let's see how to say it. The image of a continuous function on a closed bounded interval is bounded above. Alright, so if that is continuous, comma, then its image is bounded above. You with that idea? In other words, the scene doesn't take off to positive infinity. That's what we're guaranteed, as long as it's continuous and it's from a closed interval. Okay, so we'll do this proof by contradiction. 1. Assume by way of contradiction that f is not bounded above. Bounded above. Yeah. Then, for any natural number we pick, comma, there exists x in AB such that f of x is greater than n. We're assuming it's not bounded above. Therefore, for any natural number I pick, I can always get a point in the function bigger than that natural number.
Right.
Does that make sense?
Yeah. Definition of
That's our
Bounded.
medium property.
Well, we didn't use the Archimedean property. We're just assuming the thing's not bounded. What does it mean to be not bounded?
there's a number bigger.
It means for any number I pick, you should have a number bigger. So I pick some natural number, you should have a number even bigger. So that we can define the sequence xn by those numbers. So for any natural number you pick, maybe I should have said this way. Then for all n in the natural numbers, there exists an x in this interval such that f of x is greater than that n.
Right.
And then we can define a sequence of xn's this way.
If n is 1 and if n is 2, if n is 2.
Let xn be the resulting sequence. Or maybe say it this way. Let xn in AB such that f of xn is greater than n. How's that? Anything weird?
What is our n representing?
Just any natural number. The point is, for every natural number, since this thing is not bounded, then there has to be a point in here that gives me something bigger than that natural number. So there has to be some x so that f of x is greater than 1. There has to be some x so that f of x is greater than 2. There has to be some x so that f of x is greater than 3. So I can collect those xn's so that every xn, f of xn is greater than n. You with me? This could have been the same point over and over and over again, doesn't matter. The point is, now we have a sequence in AB with this property that f of xn is always greater than n. You good? Now we need to go back to the sequential compactness theorem. And what did the sequential compactness theorem say? This one was kind of weird, so let's wrap our heads around it. I don't know if we'll have time to finish this. Shoot. Maybe we'll just finish the lemma. The sequential compactness theorem said that if you have a closed interval like this, for any sequence in there, it contains a subsequence that converges to a point in there.
Oh yeah, I remember that.
Okay? It's kind of a weird one. So, since xn's in there,
Then there's a subsequence. XN.
then there exists the subsequence xnk such that the limit of xnk
Converges to X naught.
is equal to x naught is in
AB.
a b.
Is there a contradiction?
No, not yet.
Jeez.
Now, we know that f is
Compact. Compact.
no. How do you know? You don't know what compact is.
Fn.
Sequential is compact.
What did you say?
What do we know about f?
F.
What is f?
It's continuous?
It's continuous! So the limit of this thing, here's what I'm trying to get. Then the limit of f of x and k is equal to f of x naught.
Oh right.
Right, why is that bad?
Because X naught equals.
Well, this is just some number, that's fine. But we have the limit of this thing equaling some number. How do we know that's a big uh-oh?
That number has to be in A, comma B.
Huh?
That number has to be in A to B.
Okay, anything
And
about this?
A, I have.
What's the limit of f of xn?
Look, I might have a thing.
What's the limit of f
X
xn?
naught.
Huh?
X naught.
No, what's the limit of this?
F of X naught.
Isn't it?
What's the property of f of xn? It's always greater than n.
Right.
Oh, it doesn't have a limit.
Oh, it goes off to infinity. Oh, it doesn't converge. So this thing's not bounded. So is this thing bounded?
Shouldn't be.
Nope. But yet we have a convergence to something and therefore is bounded. Uh-oh.
Contradiction.
Contradiction.
Okay.
I didn't write out a lot of contradiction, but I said it, so good enough. So that's the limit. Then we got one more piece to tack onto this to finish proving it, but I don't want to try and crunch it in there because it's going to take a little bit longer than that. So read that. We'll come back and finish that next time, and we'll continue with chapter 3. Hopefully I have your test done by then so I can tell you guys what you messed